In the last video, we looked at an overview of transformations that we can use on functions and saw roughly how they work and what they do to a function. So in this video, we're going to dig into the details of those 6 kinds of transformations and how we write and apply them to a function. If you have not watched the other video, I recommend you go watch it before this one so that you have the right background information. So when we're talking about transformations of lines, transformations of any function, we start with something called a parent function. Parent function is the most basic version of whatever kind of function we're talking about. For example, the linear parent function is f of x equals x, or y equals x. So that's like saying y equals mx plus b, but y equals 1x plus 0, the most absolute basic line that we can make that's not like horizontal or vertical. It has a slope of 1, it has a y-intercept at the origin, and it's just super basic. So what we're going to do is talk about transformations in terms of either this parent function or an existing linear function. And we mentioned in the last video there are 6 total kinds of transformations. In that video, I broke them down by type of transformation. In this one, we're going to focus on separating the transformations into 2 main categories. The first category is the 3 that are vertical transformations, and the other 3 are horizontal transformations. So we're going to go through and talk about vertical first because they're the ones that seem right, and then we'll talk about the horizontal ones because they seem kind of backwards, as we saw in the last video. So vertical, the ways we can change, as a reminder, are we can translate, we can reflect, and we can stretch, which is like dilation but only in 1 dimension. We can do the same 3 things for horizontal. We can translate, but maybe we'd be more specific. So this was up and down. Here we can translate left and right. We can reflect. Here we were reflecting over the x-axis. And here we're reflecting over the y-axis. And then we can stretch. So here we're stretching this way, and here we're stretching this way. So we have names for each of these. If you're writing notes on this, I'm going to go ahead and put, let's go ahead and just dive into the vertical ones. So we're going to start with a vertical translation. So vertical translation, it moves the shape up or down. So move or shift up and down. So if I wanted my line to move up, then I add something to it. So I would do f of x. Let's write it like this. Let's say we usually call the transformed function g of x. So g of x is f of x plus something, right? We're going to add or subtract something to move the graph up or down. We give that the letter k. So k is like our vertical shift distance. If we want to move up, k is positive. So move up is positive, down is negative. So for example, think of just our linear parent function. If I said g of x equals f of x minus 2. If we take our original parent function and we take f of x, which was x, and subtract 2, then g of x would be x minus 2. And we would end up with a y-intercept of negative 2, and the whole line would be moved down 2 units because the slope stayed the same. So it would be parallel, and it would have shifted down 2 units. That's kind of boring with the parent function. So let's look at an example where we start off with f of x equals some line that's not the parent function, like 2x plus 6. If we apply this transformation to it, then we would say g of x equals whatever f of x was. So f of x was this, 2x plus 6. And then afterwards is a minus 2. So if we collect the like terms, we get a transformation of g of x equals 2x plus 4. So again, we can see that our y-intercept was 6, and now it's 4, and our slope is the same. So our line that was 2x plus 6 moved down 2 units, and now it's 2x plus 4. So this is our most simple kind of transformation we can do. We just add or subtract something at the end, and we call that thing k. So I'm going to put k here. All right, let's look next at a vertical reflection. So vertical reflection. Remember that was over the x-axis. So if we had our graph, our shape is up here. Well, I guess we're dealing with lines now, not shapes. So we have a line, say, here, and we're reflecting across the mirror line of the x-axis down here. So this green line is our mirror line, and then our reflected shape would be down here, something like that. So some observations we can make are the y-intercept used to be positive, now it's going to be negative. Our slope used to be uphill, and now it's downhill. And that is kind of the heart of how we make this change. We know that uphill has a positive slope and downhill has a negative slope. So the way that we reflect across the x-axis is we take g of x is equal to, and we just put negative f of x. So remember, f of x is our y values. So we're saying make all the y values negative, including the slope and the y-intercept. So let's use this example we had up here again, where f of x, and we're going to keep using this example, so let me highlight it. So f of x is 2x plus 6. If we wanted to apply this transformation, we would do g of x equals, and then put negative whatever f of x was. So I'm going to put this in parentheses because there's two terms, and I'm going to put 2x plus 6. We got that from this highlighted part up here. 2x plus 6 is f of x, so I can plug that in right there. If I distribute, then we see that g of x equals negative 2x minus 6, because this negative distributes to both of these, and that reversed my slope. 2 became negative 2, and it reversed my y-intercept. 6 became negative 6. So looking at our little sketch over here, it did exactly what we expected. The y-intercept switched signs, and the slope switched from uphill to downhill. So that's how we do a vertical reflection, is we make f of x negative. And that means reverse the sign of every part of it, right? Change everything from plus to minus. Last kind of vertical change we want to look at is going to be a vertical stretch. So vertical stretch, so that's going this way, is basically we're multiplying the y values by an amount. We're going to call that amount a, just because we need a letter for each of these things. We didn't need a letter for a reflection because it was just a negative sign. So a vertical stretch we write as g of x equals, and then we put a times f of x. So whatever f of x was, we multiply it by this stretch factor. So think about a graph again. If I have a line that's kind of like this, and I stretch it, the way I think of it is I grab 2 points on the line, I pull up here and down here, and I basically end up making a steeper line. So I end up with a line that looks like this versus my original one. So stretching vertically means that basically every y value gets multiplied by a, oh, I don't know how I got a star. every y value gets multiplied by that a number, so they're all getting taller. They're all getting further from the x-axis from wherever they started. So you could also see that means we're increasing our slope. So we are also changing our y-intercept. I didn't draw this very precisely at all. Our y-intercept, let's go look at one of these on Desmos real quick, just because I can't draw this well enough. So let's look at our function we've been using, 2x plus 6. If we multiply this by something, so let's say we're multiplying it by a value of 2, we make it twice as steep, so the slope increased, and notice that the y-intercept also changed from 6 to 12. So the multiplying by 2 here applied to both the slope and the y-intercept, and that's what we really want to make sure we see here. So if we, in this instance, say a equals 2, and f of x is still our original 2x plus 6 that we've been using, we would say g of x equals 2 times, whatever a is, we're saying it's 2 times f of x, which again is 2x plus 6. If we distribute, then g of x would be 4x plus 12. So that's where we're coming up with what we saw on the Desmos graph, which is the slope is double. Now it's 4 instead of 2. And the y-intercept moved up from 6 to 12. So those are the 3 vertical changes and how they affect the graph. And like I said, they're all pretty straightforward. The horizontal ones are going to feel slightly weirder, but let's go ahead and talk about those. We have the same 3 kinds of changes. So we'll start with a horizontal translation. So this is going left and right. And we call the amount we're shifting by h. So h you could think of as being horizontal shift. So we saw with up and down that the signs made sense, but here, since it's horizontal, everything horizontal feels backwards. So if we want to shift to the left, we're going to add something, and if we want to shift to the right, we're going to subtract something. So we can see that as g of x equals, and then we're going to put f of x minus h. So if we are moving to the right, we're going to do x minus something, and if we're moving left, we'll do x plus something. Really, the minus is taken care of here, but I find it easier to think of h as being the opposite thing. So let's say we were shifting 4 to the right. Then you would say h is 4. But then when we plug it in, since this says x minus h, we would put g of x equals f of x minus 4. So even though we're shifting right, we end up in our formula seeing x minus 4. All right, let's see if we can apply that. We're going to use our same function we've been using, f of x equals 2x plus 6. But we're going to apply this a little differently, because notice we're not changing f of x, we're changing just the x part, right? The part that was in parentheses as x is now x minus 4. So think of it as the 3 changes that we've done so far. We're changing output values, and these 3 are changing input values. So let's apply this transformation. We'll say g of x equals, then f of x minus 4. So anywhere we see the input value in our original function, right here where the x is, we're going to replace it by x minus 4. So otherwise, this 2, the slope, doesn't get changed at all. I don't know why I'm making that ugly. So the 2 doesn't change, so we have 2. Then we see x. So wherever x was, we're going to put a parentheses because there's 2 terms, and we're going to put x minus 4. Then after the x, we have this plus 6. This change doesn't affect the plus 6 because that's part of the output value. So this is how we apply that transformation, is we replace x by x minus 4. Then we would distribute and get g of x equals 2x minus 8 plus 6, and collect our like terms to get g of x equals 2x minus 2. So one thing about lines is that horizontal and vertical transformations look very similar. That's why in this Desmos, I limited the domain so that we could see the difference between a horizontal and a vertical change. But let's take away this limitation. If I make the blue line f of x plus 4, or minus 4 is what we did, f of x minus 4, that's the exact same thing. Let me make h of x just so I have a different function. So h of x equals, and let's think of, instead of doing a shift left and right, let's do f of x minus 8. So notice the green line is right on top of the blue line. So my horizontal shift of 4 ended up being the exact same as a vertical shift of 8. Now, that only works with lines, and only if we have a domain and range that are all real numbers. So that's why I had that limitation, so I could demonstrate the difference between the two. Real quick before we go back, let's look at a different kind of function. Let's look at what we'll cover later in the year, a parabola, and make this 2x squared plus 6. So we get this U shape. Now, and I'm going to hide these. So this U shape is going to have different characteristics whether we shift it left and right or up and down, because it doesn't have the kind of symmetry that a line does, or the kind of simplicity that a line does. So if I move it 4 to the right, you can see that it slides over here. And if I move it 8 down, it slides down here. So these are not interchangeable. It's just that lines are super boring. So when we look at horizontal and vertical changes, a horizontal translation could always be replaced by a vertical one, but that's only for straight basic lines. Other more complex functions don't work that way. Okay, so now that we're done with that little aside, we know how horizontal translations work. Let's talk about if we wanted to shift left. So let's say we want to go left 5, and we're using this function just to do one more example. We'll call this one h of x, and say h of x is f of x plus 5. Remembering that if I'm going left, I have a plus, because shifting left, h is negative 5, but when I plug it into x minus h, we get double negatives and it becomes plus 5. So if we applied that, h of x equals, we're going to do the same thing as last time. We're going to only replace the x part. We're going to leave everything else alone. So we have 2 times, then where the x was, we put x plus 5, and then plus 6. If we distribute and collect our like terms, we get 2x plus 10 plus 6 is plus 16. So that's how we move things to the left or the right. Next, let's look at reflecting. Reflecting is pretty simple, and it actually is not counterintuitive. So a horizontal reflection, which is over the y-axis, so left to right. Let's draw a picture here. And let's say we drew this line. If we reflect with the mirror line here going vertically, the y-axis, then what we should end up with is a line like this that has the same y-intercept, but our x-intercept switched from negative to positive, and our slope, just like last time, switched from uphill to downhill. So we accomplish this change by using a negative sign, just like we did before. But now we're going to, instead of putting the negative sign with f of x, we're going to say f of negative x. So we're changing the inputs to be negative rather than the outputs. So if we did that with our one function that we've been using up here, 2x plus 6, we would do g of x equals, and then again, the only thing we're changing is the input. So we have 2, and then where x was, we put in negative x, and then plus 6, just like it was in the original up here. So distributing, we would get g of x equals negative 2x plus 6. So comparing that with our graph, our y-intercept stayed the same, just like we expected, and our slope became negative, just like we expected. So it looks like horizontal reflections are pretty straightforward. There's nothing like weird and backwards about them. Unfortunately, for our last kind of transformation, which is going to be a horizontal stretch, it is backwards again. So horizontal stretch, and by the way, I haven't used the vocabulary, but the opposite of a stretch is a compression. So if we make the thing, if we stretch it out, it becomes a stretch. If we squeeze it down, it becomes a compression. So that one's going this way, and it is weird and backwards. So we call the horizontal stretch or compression factor B. So now we have our 4 letters are H, K, A, and B. And those are how we change any function in existence. So horizontal stretch, we're going to do g of x equals f of 1 over b times x. So just like the h was weird where we did x minus h, this one is weird. So instead of multiplying by the normal version of b, we multiply by 1 over b. Remember, we call that its reciprocal. So 1 over b times x. Let's look at a stretch or compression. If I try to draw a graph. So horizontal stretch. If I have this as my original function, think of grabbing it just like we did before at 2 points. So I'm going to pick this point and pull to the right, and this point and pull to the left, like I'm stretching it out to make it wider. So as I stretch it out, it's going to kind of flatten. It's going to go like this and be a flatter line than it used to be. So we expect that the y-intercept is going to stay the same because we're stretching things further from the y-axis, so this point on the y-axis won't move. But everything else gets stretched further away by multiplying x by b. So these all get further out. All right, so let's do an example. If we had a horizontal stretch by a factor of 3, then we would say g of x equals f of 1/3 x, and then we would go back to our function, which I keep scrolling away from. It was f of x equals 2x plus 6. And just like before, we're going to replace only the input. Everything else stays the same. So we would get g of x equals 2, and then where the x was, we're going to replace it by 1/3 x. And then the plus 6 stays just like it was. So we end up with g of x equals 2/3 x plus 6. Our y-intercept stayed the same, that's good, and our slope got flatter. We had a slope of 2, and now we have a slope of 2/3. So it flattened out that line a bit, and that means we can tell we applied it correctly. Just as one more example, since we haven't looked at a compression, let's do horizontal compression. So compressions are values between 0 and 1. So a stretch is when a number is bigger than 1, and a compression is where it's a fraction. So if I had a horizontal compression by 1/2, then that means I'm going to have a fraction, like a fraction. So we want to think of it, this 1 over b, not as 1 over b, but as the reciprocal. So here, g of x for our last example is going to be equal to f of the reciprocal of my compression, so 2 times x. So remember, just flip this upside down. If you try to think of it as 1 over 2, that gets really confusing. So instead, think of it as a reciprocal where we're flipping this upside down and exchanging the numerator and denominator. So 1 over 2 became 2 over 1. And then if we wanted to apply that to our function we've been using, we would do g of x equals, the 2 stays the same, so that's our slope. Then when we see x, we're going to replace it by this 2x. So 2 times 2x, and then plus 6. So our transformed function, g of x equals 4x plus 6, meaning that the y-intercept stayed the same again, but this time it got steeper. So a horizontal compression on our little picture here, let me pick a new color, would be like taking these same 2 points, and instead of pulling out on them, we're going to push in on them. We're going to squish them inward, and what that will do is make our line taller. So our line's going to be steeper, and our graph, basically, you could think of it as it gets narrower because we're squeezing it in from the left and the right. So that is all our kinds of transformations. Let's recap them real quick because that was a lot of stuff, and then we'll wrap up. So we said that we had 2 kinds of changes, horizontal and vertical. Vertical makes sense, horizontal are kind of weird. We learned about the linear parent function f of x equals x, so you could think of every line as being a transformation of that one parent function. So if my 2x plus 6 is a transformation of the parent function by doing a vertical stretch of 2 and a vertical translation of 6 up. Then we talked about each of the 6 kinds. So we said vertical translation, we call that k, and k either moves up if it's positive or down if it's negative. So if we add something to f of x, we move our graph up. If we subtract something, we move it down. Let's go ahead and talk about the other translation. So we'll go by type this time. Horizontal translation, we called h, and we said that it's weird because if we want to move left, we put x plus something, and if we want to move right, we put x minus something. So it feels backwards, but everything horizontal feels backwards. Then we talked about reflections. Vertical reflection, we put a negative outside of f of x, meaning everything in the original function becomes negative. The same thing for horizontal, a horizontal reflection. We put the negative inside the parentheses, so we're changing the inputs to negative, and that means that we only affected the slope and not the y-intercept. Finally, we had stretches and compressions. We called a vertical stretch or compression a, and that a value multiplies the entire function. So it acts on both the slope and the y-intercept to make everything steeper. A horizontal stretch or compression we called b, and that one acts inside the parentheses as the reciprocal of b, because just like our translations, it's weird and backwards. And a horizontal compression makes the graph steeper, opposite of what the vertical one did, and a horizontal stretch makes the graph flatter. So 2 more things to point out now that I just realized. One is, notice that whether it's a horizontal compression or a vertical stretch, what we end up with is a bigger number, right? So we had, let's highlight again. Let's highlight in yellow. So here, where we had our horizontal compression, we ended up multiplying by 2. And up here where we had a vertical stretch, we also multiplied by 2. So if we're multiplying by something bigger than 1, either way we're making the graph steeper. A vertical stretch and horizontal compression both make a steeper graph. Whereas if we have a fraction, either one, a vertical compression or a horizontal stretch, if we have a fraction number, like we did in this example, our graph gets flatter. The slope decreases and it flattens out toward being horizontal. And then the last thing I realized I didn't cover was talking about all of this notation we've been using. So when we're doing these things, there's some important vocabulary. So we called f of x equals x, the linear parent function, and that is the only linear parent function. It is this one. We can also have an original or a reference function. So we had that when we said f of x equals 2x plus 6. I would call that an original function that we want to perform some transformation onto that. We then wrote g of x equals, and we applied some rules to this thing. So we said something like for f of x. So notice that this says 4 times f of x, and it doesn't actually tell us what f of x is. I could apply this transformation to this function, or this one, or any function in existence. So this rule we call a function rule. And it's a rule about how we're making a change. So it's not the new function. It's not what we've changed to. It's what we're doing to it. So think of this as like where we start here. This is how it's changing. And then finally, when we applied the transformation, we said g of x equals, and we distributed the 4 to both of these and got 8x plus 24. I would call this the transformed or final function. So f of x is usually our original, and g of x is the transformed version. That's not always true, just like always the letters are kind of generic and can be used in any way. Like we could say g of x is an original and f of x is the transformed, but normal, just kind of standard practice is we call the original f and the transformed one g. So this is kind of a 3-step process here. We have what we start with, how we change it, and what we end up with. And the reason that's important is on like a quiz or a test, it might ask you, it might say, write a function rule to cause a vertical compression of 1/4 and a shift or translation interchangeable left 5. So the function rule to do that would be 1/4 f of x plus 5. So the 1/4 out here is the vertical compression, and the x plus 5 here is the shift left by 5. So so this, if it says function rule, it's going to have f of x in there somewhere. Whereas if it says to transform a function, you're going to end up with a linear equation, and notice there's no f of x in this one. And then very last thing, let's talk about if you wanted to see all of the transformations together, because we can stack them just like we did here. We can make composite transformations. So if you put everything together, we have a f of 1/b times x minus h plus k. Now, we're not going to be stacking all of these together. We may put 1 or 2 of them at a time, but we're not going to make you deal with all of them at once. Algebra 2, however, will absolutely make you do all of this stuff all stacked together. But in Algebra 1, we're just kind of looking at them more individually, or maybe a couple of them together. So we'll keep it pretty straightforward using these 6 things. So that pretty well covers our notes on transformations. Hopefully you can follow along.